So we're going to start with a partial answer to this question that doesn't actually answer the question in every case, but at least gives us a start. So we're going to begin with a theorem. And this theorem applies to matrices that are in row echelon form. So let R be in row echelon form. So I'm just going to use the letter R for the matrix instead of A, just to remind us that it's in row echelon form. So here's the theorem. There's two statements. And actually, in this case, it's really straightforward. If you want a basis for the row space of a matrix that's in row echelon form, just take the rows that contain leading ones. So the rows of R which contain leading ones form a basis for the row space. So the row space of R in particular. Or equivalently, you could just say take the non-zero rows. But to make there's just, if you write it this way, it just matches up so much better with the other statement, and it's easier to see the duality between rows and columns and how they relate. But the columns of R, if I asked you right now to guess what a basis for the column space is, you'd very likely get it if you just used the first statement as a guide and just assumed that the same pattern worked for columns. You'd end up being correct. So that the columns of R, which contain leading ones, they form a basis for the column space of the matrix R. Now, note for the second statement, it would not be okay to just simply say take the non-zero columns of R, because it's possible that all the columns of R are non-zero, yet only one of those columns happens to contain a leading one. So you can't be so relaxed with the second statement. But when it comes to rows, it would be okay to replace the first statement with just saying take the non-zero rows of R as the basis for its row space. But for the column space, you have to be careful. Say the columns that contain the leading ones. So let's do a quick example. So let's say I have the following matrix R. By the way, note that I just said row echelon form. I didn't say reduced row echelon form. It doesn't actually need to be in reduced row echelon form for this theorem to hold. It is good enough if it's in row echelon form, like this example is. So here's the matrix R, and we're going to take it to be 1, -2, 5, 0, 3, 0, 1, 3, 0, 0. You can already see it's not in reduced row echelon form because here's a leading one and there's a non-zero entry right above it. So it's not in reduced row echelon form, but it is in row echelon form. So that is your matrix R. Now if I wanted to, and let's just make instructions here. I almost went off the page. How about I just slide it like that? Okay, so find a basis for the row space of R and the column space of R. Okay, so that's what we're looking for. And I'm going to slide this up so we can have room. Maybe I'll go to there so we can still see the theorem as well. Okay, so how are we going to do this? Well, just identify where the leading ones are. So we've got leading ones here, here, and here. So there's 3 leading ones. So the rows that contain leading ones, they will form a basis for the row space. And then the columns that contain leading ones, they will form a basis for the column space. So let's write that down. So let's say I'll use B1 because we're going to actually have 2 bases in this question. So let's index them with 1 and 2. So start with a basis for the row space. So the rows that contain leading ones negative 2, 5, 0, and 3. The second row will be 0, 1, 3, 0, 0, and then 0, 0, 0, 1, 0. So that's the 3 rows of R which contain leading ones. So that is a basis for the row space. How about I just write basis for the row space of R like that? That's a better way to write it than what I was going to do. Okay, for the column space, let's call this B2. So we're just going to take the columns that have leading ones. So the first one is the first column, 1, 0, 0, 0. Then the second column, which also has a leading one, will have negative 2, 1, 0, 0, and then 0, 0, 1, 0. So that is a basis for the column space of R. All right, so that is our first theorem. It tells us how to get a basis for the row space and column space of a matrix as long as that matrix is in row echelon form. But then what do you do if it's not in row echelon form? That's the next question. And it's, well, in general, this will not work if the matrix is not in row echelon form. So we're going to need another strategy. So, and I will give that to you in the next clip because we're almost at 7 minutes.